Hello everyone, I'm Renish Varghese from the Department of Studies in Computer Science, University of Mysore. Today in this session, we are going to deal with harming code, error detection and correction technique. The harming code technique, which is an error detection and error correction technique, was proposed by R.W. Harming. Whenever a data packet is transmitted over a network, there are possibilities that the data bits may get lost or damaged during transmission. Harming code technique is used to detect the error position and correct that error at the receiver side. Before we move to the actual technique, we have to understand certain things. First, what is data bits, parity bits, even parity bits, odd parity bits. Then how do we determine the number of parity bits? How do we determine the position of parity bits, the value of parity bits? And we will learn how to encode a message by harming code at sender side and how to decode the message by harming code at receiver side. And at the end, we will solve one example using harming code technique. So first, when we come to data bits are the bits which are to be transmitted to the receiver side. And what is parity bits? Parity bits are the bits which is appended to the original data of binary bits so that the total number of ones is even or odd. It is also called redundant bit. And even parity bits, to check for even parity, if the total number of ones is even, then the value of parity bit is 0. If the total number of ones occurrences is odd, then the value of the parity bit is 1. In a similar way, odd parity bits, to check for odd parity, if the total number of ones is even, then the value of parity bit is 1. If the total number of ones is odd, then the value of parity bit is 0. How to determine the number of parity bits? We can determine the number of redundant bits or parity bits using the formula 2 to the power n 2 to the power r greater than or equal to m plus r plus 1, where r is the number of redundant bits, m is the number of data bits. So we can see one example. Suppose we have 4 bits to be transmitted. Then the number of redundant bits can be calculated as 2 to the power 3 greater than or equal to 4 plus 3 plus 1. So here the number of data bits are 4. So when we apply this into this formula, we will get 8 is equal to 8. Therefore r can be calculated using this formula. Therefore r will be 3. So when we come to the next point, determining the position of parity bits. So the redundant bits can be positioned at 2 to the power n positions, where n is equal to 0, 1, 2, 3, etc. So 2 to the power 0 is equal to 1. So we can place the parity bit at first position. And 2 to the power 1 is equal to 2. So in the similar way, the second parity bit can be placed in the second position, and 2 to the power 2 is equal to 4. So we can place the third parity bit at the position of 4, and 2 to the power 3 is equal to 8. We can place another parity bit at the position of 8. So the rest of the bits are called as data bits. So here in the diagram, at the first position we have a parity bit R1, second position we have parity bit R2, and the third position we have a data bit, because that cannot be considered as parity bit position. So we can place a data bit there, and at the position of 4 we have another parity bit R3. Then at the fifth position we have another data bit sixth position we have data bit, and at the seventh position also we have one data bit. So till we have seen how to determine the number of parity bits and how to determine the position of parity bits. Then when we move value of parity bits, how can we determine the value of parity bits? Determine the value of R1 bit. The R1 bit is calculated by performing a parity check on the bit positions whose binary representation includes 1 in the first position. So when we look into the table at the right side, we can see the error position starting from 0 to 7 and the corresponding binary numbers from 0 to 7. So when we determine the value of R1 bit, we have to check at the bit position 1 whose binary representation includes 1 in the first position. So when we look into the table, we can see 1, 3, 5 and 7. At these positions, at these binary numbers, we can see 1 as in the first position. So the value of R1 can be determined or calculated using the values at the first, third, fifth and seventh positions. When we come to the R2 bit, the R2 bit is calculated by performing a parity check on the bit positions whose binary representation includes 1 in the second position. So when we look into the table, 1 occurs in the second position are 2, 3, 6 and 7. And come to the R4 bit. R4 bit is calculated by performing a parity check on the bit positions whose binary representation includes 1 in the third position. So look into the table. We have 4, 5, 6 and 7. The 1 once comes in the third position. So R1 can be calculated using 4th, 5th and 5th, 6th and 7th bits. So how do we determine the value of parity bits? R1 bit can be calculated using the positions 1, 3, 5 and 7. In a similar way, R2 can be calculated using the positions 2, 3, 6 and 7. And R4 can be calculated using 4, 5, 6 and 7. The next, encoding procedure. Encoding a message by Hamming code. The procedure used by the sender to encode the message encompasses the following steps. Step 1. Calculation of the number of redundant bits. We have already seen how to calculate the number of redundant bits. Step 2. Positioning the redundant bits. That also we have learned in the previous slide. And step 3. Calculating the values of each redundant bits. All these 3 steps we have already learned. Once the redundant bits are embedded within the message, this is sent to the destination. These are the procedures in the sender side when we encode a message by Hamming code. So the decoding procedure, decoding a message in Hamming code. Once the receiver gets an incoming message, it performs recalculations to detect errors and correct them. The steps for recalculation are: step 1. Calculation of the number of redundant bits. Already we have learned. And step 2. Positioning the redundant bits. Step 3. Parity checking. And step 4. Error detection and error correction. These 4 steps will be clear when we look into the example. Okay. Next we have an example. Example in the sender side. We have a data 1010. This data to be transmitted to the receiver side, and using Hamming code we have to check whether there is an error in the message. If there is an error in the message, we have to correct that error. That is the purpose of this technique. So in the first step, calculation of the number of redundant bits. As we have already learned, We can calculate the number of redundant bits using the formula 2 to the power r greater than or equal to m plus r plus 1. Here we have 4 bits, so the redundant bits or r will be 3, because when we substitute the 4 in the formula, 2 to the power 3 greater than or equal to 4 plus 3 plus 1, that is 8. 8 is equal to 8, therefore r will be 3. So the number of redundant bits are 3. When we come to the second step, positioning the redundant bits, already we have learned how do we position the redundant bits. In the right corner we have the diagram, and we have diagrammatically represented the position of the redundant bits and data bits. So in the first position we have r1, the first redundant bit, and the second position we have r2, the second redundant bit, and the third position we have the first data bit, and the fourth position we have the third redundant bit, and fifth position we have the second data bit, sixth position we have third data bit, and at the seventh position we have the last fourth data bit. When we come to the step 3, calculating the values of each redundant bit, we have already learned how do we calculate the values of each redundant bit. Here when we come to the value of first redundant bit r1, we check the positions 1, 3, 5 and 7. Since the number of ones are even at these positions, the value of r1 will be 0. So in the second diagram we have already diagrammatically represented the values of parity bits and data bits. So r1 is equal to 0. When we come to the second parity bit, it can be calculated with the positions 2, 3, 6 and 7. Since the number of ones are odd, the value of r2 is equal to 1. We check at the second position. Second position we have 1, third position we have 0, sixth position we have 0, and seventh position we have 1. So we have 2 ones, which means the number of ones are odd. Therefore we have to add one more 1 to make it even, since we are checking for even parity. Generally we use even parity in Hamming code, but we can use odd parity as well. So at the value of r2 will be 1. And when we check the r4 value, we have to use the positions 4, 5, 6 and 7. Since the number of ones are even at these positions, the value of r4 will be 0. Let's check. At the fourth position we have 0, and fifth position we have 1, and sixth position we have 0, and seventh position we have 1. So we have 2 ones, so no need to add any 1 to make it even. So we can write the value of r4 as 0. So first 3 steps have been calculated. So we have a message 1010010. So that message, that bits will be transmitted to the receiver side. So we have 4 bits data, and we have 3 redundant bits. Altogether we have 7 bits. So these 7 bits data will be transmitted to the receiver side. Okay, so let's see the receiver side. At receiver side we have the data 1010010. Since we have to check the error, and we have to correct that error, so we are making an error in the actual data. So we have 1010010 as the actual data, so we make a mistake in the actual data, we make it corrupted. At the fourth position we change the value 0 to 1. So the corrupted data will be 1011010. So we can see the steps. Step 1, calculation of the number of redundant bits, as we have already learned, and we have done it in the sender side. So we calculate the number of redundant bits. Since we have 3 bits data, the redundant bits, since we have 4 bits data, the redundant bits will be 3. So altogether we have 7 bits data. Step number 2, positioning the redundant bits. we know how to position the redundant bits. We have already positioned the redundant bits at the first position, second position, and fourth position. Next, we have parity checking. We have to check the parity. How do we check the parity? R1 is equal to 1 comma 3 comma 5 comma 7. Since the number of ones are even, the value of R1 is equal to 0. Let's check. At the first position we have 0, and third position we have 0, fifth position and seventh position we have 1. We have two ones, so the number of ones are even, so no need to add 1 to that, so the value of R1 will be 0. And when we come to the position 2, R2, we have to check the positions 2, 3, 6 and 7. At second position we have 1, third position we have 0, sixth position we have 0, and seventh position we have 1. So we have two ones, so the number of ones are even, therefore the value of R2 is also 0. When we come to R4, we have to check the positions 4, 5, 6 and 7. Let's check. At the fourth position we have 1, fifth position we have 1, sixth position we have 0, seventh position we have 1. So altogether we have 3 ones. Therefore we need to add one more 1 to make it an even number. Therefore, since the number of ones are odd, the value of R will be 1. So here R1 is equal to 0, R2 is equal to 0, R4 is equal to 1. So R4, R2, R1, the value will be 1, 0, 0, and the corresponding decimal value is 4. Therefore the error occurs in the fourth bit position. Actually we have the data 1, 0, 1, 0, 0, 1, 0, but we have already made it corrupted. So the data will be 1, 0, 1, 1, 0, 1, 0. At the fourth position we have found one error. So the bit value must be changed from 1 to 0 to correct the error. So in the corrupted data we have 1 at the fourth position, and we have found the error occurs at the fourth position. Therefore the bit value must be changed. We have only two values, 1 and 0 and 1. Therefore the bit value, if the error occurs at the fourth position, we have to change that bit. Since the bit value is 1, we have to change to 0. Therefore we get 1, 0, 1, 0, 0, 1, 0 as the original data without error. So that is the Hamming code error detection and error correction technique. So in this presentation we have learned what is Hamming code technique, data bits, parity bits, even parity bits, odd parity bits. Then we learned how do we determine the number of parity bits, determine the position of parity bits, determine the value of parity bits. Then we have learned how to encode a message by Hamming code at sender side. We have learned what are the steps to decode a message by Hamming code at the receiver side. And at the end we have learned, we have seen, we have solved an example using these Hamming code techniques. I hope everything is clear for you. So thank you for watching this video. Thank you for your patient listening. Thank you very much.